We are almost done with the course, okay? I'm hoping this would be one of the last lectures to cover material for the final exam. I'm hoping I finish with this. That will end the material to be on the final exam. And then the remaining lectures we're going to dedicate to review, machine learning, and a few other activities to wrap up the semester. So I'd like your attention here. We're almost done with ordinary differential equations. We did initial value problems so far. To give you like a bird's eye perspective, those with initial values, we dealt with explicit methods like the forward Euler method, and we looked at an implicit method such as the backward Euler method. There are many other methods. So you might be given actually on the homework, you will be given another method called the Crank-Nicholson, which combines both an explicit and an implicit method together and kind of takes an average. But it's still an implicit method. Implicit methods always, in general, result in a nonlinear system of equation, and a nonlinear equation to solve. We looked at solving systems of equations. We learned about ODE int. We programmed forward. So we did a lot. Like if you were to compare yourself, and we'll talk about this at the last lecture. If you were to compare yourself today to where you were at the beginning of the semester, that's a great way to assess how much you've learned, how much you were exposed to at least. Even if you didn't master the material or every piece of material we covered, it's important to take a look and see that if you've improved in terms of gathering this knowledge that was essentially vomited here in this class. So much to cover. And I know you have other courses and a lot of other things to cover, but this course is the most important one, of course. Well, at least every professor thinks their course is the most important, but they all contribute to your learning. Okay, so we're doing our best, but we come with the best intentions that, this is important material. You're going to see it. At least I go to sleep comfortable thinking that my students have been exposed to programming and numerical methods. They can talk with computers. They're going to land. All jobs now have a data science element to them. And so I go to bed comfortable thinking that, I've given you the best I can. All right. The last piece of the puzzle in ordinary differential equations are boundary value problems. If you go back to the classification of ODEs, we looked at initial value problems where you have the state of a system initially, such as you put some reactants together and tell them go. They start reacting and talking and doing fun things. Okay. The boundary value problems, on the other hand, you don't specify the initial state of the system. Instead, you only specify the state at the boundaries of the system. Okay. So boundary value problems are typically associated with things that evolve or in space, that change in space from one point to another, whereas initial value problems are associated with things that change in time, starting with an initial population of infected people, for example, and uninfected people. How does that system evolve over time? Okay. When you combine the two, you get partial differential equations. Okay. All right. So this is a graphic of what a boundary value problem looks like. You typically have some boundary, some physical boundary where conditions are specified, temperatures at the boundary or the speed of the air at that door over there and at the inlet vent up there, right? So you specify information at the boundary and see what happens inside the physical system, okay, in space. We did this actually. So half of this lecture, what I would have spent time to cover here, we already did all of this in linear systems, okay? So that's why we covered the heated rod example, if you remember. That exact problem where we had temperatures fixed at the boundary and maybe a heat source in the middle, blowing air at the rod, or you're heating it up. It's all the same. It's a boundary value problem. So we've seen this before, okay? So it's good. We're going to revisit it now and go a little bit under the hood like I promised you. In this case today, we're going to consider one of the problems we solved with the heat transfer, and that's called the convective heat transfer, where the rod is fixed at temperatures at each end, T at the left boundary and T at the right boundary, and there's air blowing on the rod. So that air, depending on its temperature, which is T infinity, it could either cool the rod or heat it up, okay, depending on the temperature of the air that's blowing. And the equation looks like this. Now, again, you're not concerned about how that equation is obtained. You will learn that in your heat transfer course, okay, and in your mass transfer courses, all right? But I'm going to teach you how to solve this equation numerically, so you're ready when you go take those courses. So this is the equation for the convective heat transfer problem. It's a boundary value problem. Why? Because you specified the temperatures at the boundaries. You're blowing air at it. Depending on those temperatures, the temperature inside the rod is gonna have a distribution. It might be cold over here, might be hot over here, somewhere in between in the middle. It might be hotter in the middle and cooler at the edges. It's a strictly boundary value problem. It's how the temperature changes along the rod, okay? So this would be the mathematical formulation of this. HP over lambda AC are parameters for this problem. Lambda has to do with heat diffusion. H has to do with heat convection. P is perimeter, and A is the surface area. So don't worry about those. Those are just a coefficient, okay? Now, there are many ways, or just a few ways, to solve a boundary value problem. There's something called the shooting method, which is very complicated and very annoying to implement. Our approach, the approach we're going to take in this course, is using finite difference methods to solve boundary value problems, just like we did with the initial value problem. Okay? So I'll guide you step by step on how we're going to do this. So we're going to consider this heated rod, okay, with temperatures fixed on both ends, and we're going to call that entire coefficient HP over lambda AC. We're going to call it just capital H, bless you. We're going to call that capital H, okay, for simplicity. And the rod is heated starting x equals 0 to x equal L. T left and T right are the temperatures. They're known. They're given to you. Okay. So based on what we did with initial value problems, what was the first step? What is the first step we need to do to convert this equation into something that we can manipulate numerically? Discretize it. Thank you. So we're going to discretize this equation. Now, discretizing this equation also means discretizing the space domain. Just like we did for the initial value problem, we discretized the time domain. We started from t equals 0 and then t0 plus delta t, that's t1, and then t1 plus delta t, and so on. So we split the time domain into a number of intervals. We're going to do the same thing here. We're going to split the rod into n equally spaced points. The spacing is delta x. It doesn't have to be equally spaced, but to be able to do what we want to do, we just do an equal spacing here. Now we're going to assign an x value at each one of those points. So just like the time value for the coordinate in time, this is the coordinate in space. And we did this also in linear systems, right? So at each one of those points, you have an x value starting with x0, and then x1 equals 0. And then x1 plus delta x, that's x2, x2 plus delta x, that's x3, and so on. Okay? So those are the x values. Okay? Why do we need that? Because if your right-hand side, or if there's a source term that depends on x, that source term needs to be evaluated at the right point where the ODE is being discretized and evaluated. Then we're going to assign a variable for the temperature value at each one of those points, starting with T1 equal T left, which is given to you, and then a bunch of unknown temperatures in between, and finally the last point at N, which we call Tn, and that's also given to us as T right. So you have the T left and T right temperatures given to you, and this entire process discretizes the space domain. Next, we're going to discretize the equation itself. Okay, now before we discretize the equation, I'll ask you this question. And that question was asked with the initial value problems as well. Is this governing equation that governs the heat transfer inside the entire rod from the left boundary to the right boundary, is it valid at each one of those discrete points? Yes, of course. Why not? These points are a subset of the rod, right? If that equation is valid anywhere in the rod, it should be valid at any one of those points. So indeed, this equation is valid at any one of those points. So at point 2, you can write d2t by dx squared at point 2 is equal h t2 minus t infinity, right? And that is t2 exactly, okay? Because we evaluated that equation at that point, right? Same thing for point 3, and same thing for any point inside the domain, right? For an arbitrary point I, that equation d2t by dx squared, second derivative of temperature, at point I is equal to h times ti minus t infinity. It's critical to recognize how we applied everything at point I, okay? T infinity is not at I because T infinity is fixed everywhere. It's the same, it's a constant. Okay, so now we're gonna discretize, okay? And by discretizing, what we're gonna do, we're gonna approximate that second derivative, right? On the right-hand side, we don't have any derivatives, so there's no approximation going on. But on the left-hand side, we have the second derivative. Do you remember the approximation? If you pull up your notes, can you give me the approximation that we can use for the second derivative? Central discretization. It is second order, yeah, by this. The simplest one is second order. So if you pull up your notes, what is the approximation for the second derivative at any point I? You can pull up your notes. So that's a formula, for example, might be useful to put on your note sheet for the final exam. Okay, those finite difference formulas. Okay? Because that's not the only way to discretize this equation. You could have higher order discretizations. Okay? But for now, just a second order discretization for the second derivative. What is it? Okay? It's ti minus 1 minus 2ti plus ti plus 1 over delta x squared, right? So we're using point I, the value at point I and the neighboring points to approximate this derivative. Now what's interesting is that we don't know those values, right? When your homework for finite difference methods, you had values for point I minus 1, I plus 1, and you plugged on those values to approximate the derivative. Here we don't know those values, but that's okay because we're gonna build a system of equations with these unknowns, okay? Like we did with the linear systems of equations. So this is nothing new. We covered all of this in linear systems, if you remember. The only difference is that now you know how this was converted to this because we studied finite difference methods. That's all. So this is more of a review for linear systems. Now you can rearrange this, multiply by delta x squared, and put all the unknowns on the left-hand side, and then we have all the ingredients to solve this system of equation, this equation, okay? So here's the activity, apparently. We now have all the ingredients to solve for the unknown quantities, T2 all the way to Tn minus 1. Explain why we have all the ingredients and what are we going to do next. So if you take this equation, it's valid so at point 1, we know the value. We know T1 is equal to T left. This equation applies at point 2, point 3, point 4, all the way to point n minus 1, right? So is this enough to solve for all of those variables? Yes. Yes. Because we did it before. Because if you cannot see it yet, this is just a system of linear equations. At point 1, T1 is equal to T left. At point 2, you apply that discrete equation. It's just T1 minus 2 plus h delta x squared, whatever, times T2 plus T3 equal minus h delta x squared T infinity. And then at point 3, again, you apply that discrete equation, the one above, up there, right? And then all the way to the last 2 points. At point n minus 1, you get this equation. And then you need one more for Tn. So all in all, yes?
If we're solving for the temperature directly, why are we using the second order derivative, the second derivative?
Because that's the governing equation. So we're solving this equation, right? And that equation is given to us as a second derivative. So are you asking about order of the discretization?
Yeah.
So this discretization, this is the lowest order discretization you can get for a second derivative, right? So you cannot just, and unlike time, you can't do Tn plus 1 minus Tn. You cannot march in space like that. So with time, with an explicit method, we were able to do Tn plus 1 as a function of everything in terms of Tn. right? But that was time because that was a first derivative only in time. But in space, you don't have that kind of simplicity. In space, everything is coupled to everything else, right? So that's why you have I plus 1 coupled to I minus 1 and coupled to point I. So they're all tightly connected with each other. Connor?
Could you also solve this given just two random temperatures in the middle of the rod? Would that be?
So no, those would be, you cannot, that will be an overdetermined system. Yeah, that will be an overdetermined system. So you'd have to split it into multiple boundaries. But yeah, that you have more boundary conditions than you need to fully specify the problem.
So T left and T right would be known constants?
Yes, those are known constants given to you. Those are the inputs specified at the boundary. You can always rely on that.
So if this were in like 3D space, like if we had three directions, would it be like third order derivative?
No, you would have 3 second order derivatives. d2t by dx squared, d2t by dy squared, and d2t by dz squared. You would have a Laplacian, actually. And then you would have to approximate each one of those derivatives, and you'd have 3 indices, I, j, k. It gets much more complicated. Okay? Now, these are n equations and n unknowns. You can count them. These are 1 equation, 2, 3, etc., n. N equations with n unknowns. So that's a fully, and all of these equations are linear, like we did with the linear systems of equations. And lo and behold, this results in the classic tridiagonal system of equations that we all know and love and learn how to solve, okay? But now we're not going to do Thomas algorithm or anything. We're just going to do numpy.linalgebra.solve, okay? So we're not going to worry about that. And so if you remember what we did in January, we built this, once you have this system of equations, it's repetitive, right? All the entries are the same, almost all of them. So you can just build them using diagonals, if you remember doing that. All right? And let's go ahead and do it again, one more time. So we're going to now solve this heat transfer problem for an arbitrary number of points n, okay? And we're going to play around with the temperatures. This is, again, a review. We did this problem in linear systems, okay? So this is only just a little review, but it's good to refresh our memory. All right, so let's create a new notebook. I highly advise you to create new notebooks for each, a new notebook for each problem we're solving. Okay. So we're going to get our boilerplate stuff. Let's see. Okay, so boundary value problems with Professor Saad 2023. I have like 1,000 of these notebooks every year. So I decided to have a very unique nomenclature now. 2023, 2024. So I know I don't get confused. Okay. So what we need, let me get the slides up there. Okay, so we need to solve, essentially we need to implement this entire matrix, right? So for that, we're going to need a number of points, which is going to determine the number of equations. We're going to need to specify a coefficient, h, okay? And once we specify the number of points, delta x is automatically inferred from that. And we need to specify t left and t right, okay? So let's suppose, you know, we said, say, n equal 200 points, okay? And let's specify our rod length is 1 meter. Okay, t left is, let's say, 300. T right is 200, whatever. And T infinity, which was another variable we need to specify, that's the temperature of the air blowing on the rod. And our H is 10. That's some heat transfer coefficient. Okay. Next, I would like to create the CC, whatever, however you spell that, the X values. X is equal to mp.linspace 0 to L with n points. Okay. Now from that, because that's equally spaced, you can infer your spacing. dx is the difference between any two values in that linear space. Okay. So that specifies the physical problem. Now we create lower diagonal. Create lower diagonal, which is lower diagonal is MP dot ones of size n minus 1. If you remember, that's the lower diagonal. We have ones everywhere except the last entry, which is 0. So we create an array of ones, okay, of size n minus 1. And then we say the last entry is 0. Then create main diagonal. Main diagonal is D, and that's equal minus 2 plus h times dx squared, okay, times mp dot ones of size n. So that's the main diagonal. It has n entries in it, okay, n entries. All of them are minus 2 plus h delta x squared, except the first and last entry is there 1. Okay, so D0, that's the first entry, is 1, and D last entry, D minus 1, is 1. Okay, and then finally lower diagonal, upper diagonal. Upper diagonal is upper diagonal mp dot ones of size n minus 1. Okay, and upper diagonal 0, that's the first entry in the upper diagonal, is 0. Okay. That's great. And then if you remember, we can build the full matrix by calling mp.diag for lower diagonal minus 1 plus mp.diag for main diagonal 0 plus mp.diag for upper diagonal 1. So mp.diag takes a vector and places it on this diagonal. So this, we're going to take the lower diagonal vector and place it on the lower diagonal, which is minus 1, because we start counting diagonals from the main diagonal. The main diagonal has always index 0, upper diagonal has index 1, lower diagonal has index minus 1, second upper diagonal has index 2, and so on. Okay? All right. Now we need to build the right-hand side. Okay? Right-hand side vector. RHS is minus t infinity times dx times h times mp dot ones of size n. Right? If you look at the lower diagonal, at the right-hand side, sorry, all of the entries are minus h delta x squared t infinity except the first and the last. So we create this vector of size n, and then we fix the first entry, which is t left, and the last entry, which is t right. And okay. And then we solve it. Solution is mp.lin algebra dot solve. A right-hand side. And then we plot it, plt.plot, x solution, plt.grid. See? Oh, there you go. Okay. Quick sanity check. T left is 300 indeed. T right is 200. We got air blowing at 500 degrees. It's trying to push it to 500. So things are same. It's a good sanity check. Okay? And like we did previously, you know, you can play with the temperatures, etc. So there's really nothing new over here. Okay? There's nothing new going on here. But I needed to repeat this problem because now we're going to make it a little harder. Okay? So I'll give you a minute to catch up. A minute to catch up. All right. Any issues? Yeah, that boilerplate, it's like always a good idea to keep it somewhere like in your notes or something.
That's not right.
Pardon me? Yeah. This is good?
So mine did this. I assume I did something wrong.
Yeah, your yes, so upper diagonal.
I said upper diagonal, you can lower diagonal.
No, that's nope, because that is gonna change your lower diagonal. Just create a fresh one. Yeah. Okay. Are we in sync? All right. Let's make it a little harder, shall we? Okay. All good and fun with the world. However, that's not the only story with boundary value problems. Oftentimes, with boundary value problems, it's very hard to physically fix the value, especially like something like temperature. It's almost impossible to keep the temperature held at a fixed value. What we find oftentimes is that we can, instead of fixing the value of the temperature, we can fix the rate of heat transfer, how fast heat is being added or removed. Okay? And that changes the character of the problem as follows. So what we've covered so far are what we call Dirichlet boundary conditions. Because these are boundary value problems, boundary conditions are going to matter. There are two general types of boundary conditions. The Dirichlet type boundary condition is one where you specify the value of the dependent variable, the value of the variable that you're solving for at the boundaries. Okay, so that anchors t left and t right. You specify those, you're done. That's a type of Dirichlet boundary condition. There's another kind of boundary condition, which is called a Neumann type boundary condition. Okay? And in Neumann type boundary conditions, you specify the slope of the variable instead of the value of the variable at the boundary. In other words, you specify the rate at which you're either feeding or extracting that value. So for temperature, specifying the slope of temperature means you're specifying the heat flux, how much heat you're adding or how much heat the rate at which heat is being added or subtracted from the domain. Okay, so that complicates things at the boundaries. Right? So far we covered Dirichlet boundary conditions. That's what we did with linear systems of equations. So now we're going to go a little bit deeper and try to figure out how we're going to handle Neumann boundary conditions. Okay. Again, we're going to take the example of the heat transfer problem, but that's not the only example you're going to be dealing with in your homework or in your exam. Okay? Because now you know how to discretize, how to apply a second derivative approximation or a first derivative approximation, combine them, etc. So try to learn this quite well, okay? So in this case, now, at the right boundary, you don't have Tn anymore. You have dt by dx at point n is given by some value, some constant value beta, okay? So our previously discretized equation, all the way from point 1, t1 is t left, all the way to point n minus 1, that still holds. Nothing changes. Okay, did you have a question? Okay. But something different needs to be done at the boundary to the right, okay? So for Neumann conditions, we're going to say, okay, we don't have the value of the temperature. We just have the slope of that temperature. We really can't do much with that. But we know that that equation up there and its discrete version does apply at that endpoint, okay? So let's try and apply it at that endpoint. So if you go and apply it at that endpoint, n, you get Tn minus 1 minus something times Tn plus Tn plus 1. But that's a problem, because we don't have Tn plus 1. Right? I see some panicked eyes, shut down the laptop, leave the classroom. Okay. Well, not quite. It's not going to work, because now you have one more degree of freedom. Right? So this Tn plus 1 doesn't really exist. However, just suppose, okay? So, okay, Miles has a great idea. So do a backward discretization, okay, at that point n. That's one way of doing it. The other way I want to do it is to actually create that fictitious point, okay, called Tn plus 1. And actually, we call that a ghost point. Literally. It's called a ghost point. If you look at the literature in computational fluid dynamics and advanced numerical methods, they call it ghost point. And sometimes that orange box over there is called a ghost cell. And one time, some person was reviewing, my proposal, like, what's a ghost cell? Is it a cell where you lock up ghosts? Lol, So anyway, that's the joke. Anyway, that's a ghost point, okay? And it doesn't really exist. It's not part of our solution and doesn't really add anything except allow us to mentally do some mathematical acrobatics to allow us to get rid of that Tn plus 1. Okay, so now we added one more degree of freedom. That's Tn plus 1. Now we need to eliminate it, okay? That Tn plus 1 doesn't exist. We're just only assuming it exists for a minute, okay? So that we can figure out a way to eliminate it. Now, we bring in one more piece of information. We haven't used the boundary condition at all yet, right? What if we take the boundary condition itself and also discretize it? Okay? Approximate the derivative with a suitable discretization scheme. Since everything was second order we've done so far in the interior domain, we need at least a second order discretization here to maintain global order. So we can't do a first order derivative. We need a second order derivative here. And this second order derivative approximation is this one, Tn plus 1 minus Tn minus 1 over 2 delta x equal beta. Okay. So now we added Tn plus 1 over there, but we have one more equation for Tn plus 1. So essentially, we've closed the system. Okay? We found one more equation for that ghost point, right? So we added Tn plus 1, which was one more unknown. We needed one more equation for that Tn plus 1. We didn't make it up. We used that point as a ghost cell. Now we're gonna solve for Tn plus 1 over here in terms of Tn minus 1, which is part of the variable. We're gonna plug it back in. We don't have Tn plus 1 anymore.
But we made up Tn plus 1 as the ghost point.
Yeah, but it doesn't really matter at the end of the solution, right? We only used it temporarily as a figment of our imagination, okay, to allow us to do the math, and then we're gonna eliminate it. So if you solve this equation for Tn plus 1, and then substitute it back over here, you don't have Tn plus 1 anymore. Right? The last equation at the boundary doesn't have Tn plus 1 in it anymore. So we only created Tn plus 1 to allow us to do the math. But programmatically, it doesn't exist. You don't need to store a variable in it. You don't need to do anything about it. Because that's the equation at the boundary now, at the right boundary. Todd?
Is there a reason we're able to make a ghost point equation that we know the slope is at?
We know the slope at that boundary. Yeah, and we're going to approximate that slope using a suitable finite difference scheme. Okay? So really, I needed some more information at n plus 1. Right? So my discretization for that slope at n, I wanted to use Tn plus 1 so that I can eliminate the other Tn plus 1. Okay? So once you do this now, you still have your standard system of equations from first point all the way to n minus 1, and then the last point, you just have a different equation. Okay? And you can put this into a system of equations and solve it. So this is what happens. When you substitute these equations, convert them into matrix form, you get that same tridiagonal structure. The coefficients are the same, except for that last point, the right-hand side is a little different. Okay? So that's what matters here is this pattern. So now let's go back and add a Neumann boundary condition for the heat transfer in the rod. Okay? So the only thing that's going to change is this last entry in the right-hand side. Okay, so I'm going to take this now, and I'm going to copy it. I'm going to create a new text cell and say heated rod with Neumann boundary conditions. Okay. So I got everything except for the T left is still 300 or whatever value you want, but on the right, I don't have T right. I have the slope, which is beta. Now, that beta slope it's literally just the slope of the temperature. So if we set it at 0, it's going to be flat. The temperature profile should be flat at the right boundary. If we set it to a negative value, it's going to go down. If we set it to a positive value, it's going to go up, right? So you're either adding heat or extracting heat. So let's start by setting it at 0. Doesn't matter. We'll change it. Everything else stays the same, guys. Nothing changes except for the right-hand side. Okay? The right-hand side, now the first entry is T left. All the other entries are the same, except the last entry now is minus h delta x squared T infinity minus 2 beta delta x. So all I need to do here is subtract that with 2 times beta times delta x, right?
Is it minus?
Yeah, so because RHS already has the first term in it, right? So look. The first term here is this guy, right? It's minus h delta x squared T infinity, which I already reset it, and then I'm going to subtract this piece from it, okay? If you don't like that, just write the whole right-hand side. Yes, Mark. A beta is the slope. Oh, I put 0 right now. I just put 0, okay? And that's it. Okay, so hold on. Made a mistake. That is clearly, okay, beta T infinity, and then h, hold on. Did I miss something? Nope. T infinity delta x squared, okay. Yeah, beta is already set to 0, right? So, yeah, that's just fine.
So it should still be the exact same.
No, because the other one was T right. No, it shouldn't be the same at all. So there is something.
It's T right minus 0, right?
No, because RHS is initialized to this, right? Yeah. So I have a typo somewhere. Let's see. So upper diagonal, main diagonal. Well, it's supposed to be flat at, yes, I made a mistake here. Look. Yes, there's actually the lower diagonal has a 2 over here, and the main diagonal has this over here. So that's what changed as well. My bad. Okay. So if you look over here, the last entry in the lower diagonal is no longer 0. It's actually 2. So in the lower diagonal, this should be 2. And on the main diagonal, we don't change the last entry anymore. Okay, there you go. 300 on the left, which is the temperature. So I did this on purpose, so I make a mistake. No, these are the best errors that occur because, that's how debugging works, right? So 300 is still fine. Okay, that's T left. But then on the right, my slope is 0. And indeed, that temperature is trying to get to 0 over there. To a slope of 0. Okay? So now if I put a negative value for beta.
So this is like if the T right doesn't have a set value.
Exactly. It's a rate at which you're extracting heat or putting heat. So now if we put a negative value for beta, let's say minus 50, okay? Look at that. It's starting to go down. It's starting to slope down because we are extracting heat. A negative value is going to mean we're extracting heat. It's going to start causing the temperature to drop. You can keep increasing that value, 500. Okay? Look at that. It's starting to go really down. So there's no set value for T on the right. You're setting a rate at which T is being extracted or added. Okay? Okay? Now, if you swap that sign for beta, then it's going to start going up. Look at that. Slope is positive. Okay?
So the second one, instead of being given T right, we're finding T
Sure, you can deduce t right from it, but you're only given the slope, right? But yeah, the system is going to solve for t at that boundary. Okay, it's no longer a fixed value anymore. Okay. Let's see, we're doing on time. Okay. Okay. So now you should be able to do this procedure for any ODE any boundary value problem I give you with any combination of boundary conditions. We could put a Neumann on the left and a Dirichlet on the right, or two Neumanns, one on the left and one on the right. We could add a first derivative to the boundary value problem. So let's do a couple of examples, okay? It's very important that you work these examples, okay? It's very important that you work those examples. Okay, so here's an example where I have this second order differential equation. It's a boundary value problem. d2u by dx squared equal x squared u. Okay? So the right-hand side depends on u, which is the unknown we're trying to solve for. And we're given the boundary conditions, a Neumann on the left, du by dx equal alpha, and a fixed value on the right, kun equal beta. Okay? There's no tn on whatever, it's only u's. Okay? So in this case, so what I would do first is just discretize the interior. Forget about the boundary conditions. Let's just discretize the interior of the domain. So if you were to discretize the interior, you just apply that discretization formula we have for the second derivative, or take that equation, apply it at an arbitrary point I, apply the discretization. Now pay attention to the right-hand side. The entire right-hand side is everything is applied at point I, the point at which you are discretizing. So x, you have u, you have sine u, everything is at I, at point I. Okay, so that's why you see xi squared times ui. Okay. Then you can simplify this equation like that. Okay. All right. At the left boundary, what do? We write the discretized equation at the Neumann boundary. So go ahead and do that. Write this equation at point I equal 1. You're going to end up with a ghost point u0, but that's okay. We're going to eliminate that ghost point. Yeah, do it by hand, please. Yes. So again, it's very important that you practice these over and over again. There's only like a few ways I can make this complicated. I can put two Neumann conditions, one on the left, Dirichlet on the right, Dirichlet on the left, Neumann on the right. You can add one more derivative, make the right-hand side, slightly weird, but that's it. Only a few ways we can make this complicated. So write the discretized equation. This is the discretized equation. Now apply it at point 1, at I equal 1, at the left boundary. Because we don't have information at the left boundary. We only have the slope. We don't have u specified at the left boundary. Yeah, so I would write the whole thing equal 0. Right, so put everything on the left-hand side.
Oh, okay.
Yeah.
So, but it is
Because we're not trying to find u0.
we're trying
Okay. No, yeah, we're trying to find, u0 is not part of the solution. u0 is just a temporary step, okay, to allow us to, our objective is to find u1 to un. We're not finding u0, so keep u0 on the left-hand side, and then we're going to eliminate it in the next step. Still working on it? Just apply this equation at I equal 1. You get u0 minus whatever. Just put I equal 1 in there. If you put I equal 1, you get u0, which is our ghost point, shown in red here to stress that, minus 2 plus delta x squared, x1 squared times u1 plus u2. Okay? So u1 and u2 are part of the solution process. We're trying to find them. u0 is not. Doesn't exist. However, we have one more piece of information that we can use to eliminate u0, and that's the boundary condition du by dx at x equals 0. Okay? So that du by dx equal alpha. So now eliminate u0 by discretizing, so discretize the Neumann condition at that boundary. So convert du by dx at 0. It's u2 minus u0. Yes? This one? This one? It's this one rearranged, right? So I just multiplied by delta x squared, moved this term over here, and combined them. So I write coefficient times unknown, coefficient times unknown, coefficient times unknown. Yeah, that's what we do with the linear systems, right? Okay, so now if you were to eliminate or approximate that derivative, you get u2 minus u0 over 2 delta x equal alpha. u2 is part of the solution. You know alpha, you know delta x. So then you solve for u0 in terms of the other solution variables. So now we express u0 in terms of u2, and then we substitute. So you take this u0, which is u2 minus 2 alpha delta x, and put it in here, and then you derive the equation at the left boundary. Now always rearrange it as unknowns on the left-hand side with their coefficients, and everything you know on the right-hand side, because these are linear, going to be linear systems. Okay? And at the right boundary, you know that un is equal to beta. Okay? That's given to you. That's a Dirichlet condition at the right boundary. That's it. That's all you have. So in the homework, in the exam, I will ask you, what is the equation at the left boundary? What is the equation at the right boundary? What is the equation in the interior? And then if the system is linear, put it in matrix form, okay, which is going to be the next question. So now express this in matrix form. So your unknowns are u1, u2, u3, all the way to un. Okay? So write it in matrix form now. And in matrix form, all I need are the coefficients in the coefficient matrix, the the unknowns, the solution variable vector, and the right-hand side. You should always assume endpoints, okay? If I don't tell you otherwise. I might tell you do it for 5 points, for example. But in general, assume endpoints. So you put the 3 dots, dot, 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 okay? Okay, I'll help you with this one. So first thing you do is, first thing when you're building this matrix is you write this so that you know what your unknowns are. u1, u2, 3 dots, un minus 1 un. Okay? You start with the first equation. The first equation, that was the equation at the left boundary. What is the coefficient of u1? It was minus 2 plus delta x squared times x1, if you go back. Right? That was the coefficient of u1. What is the coefficient of u2 is 2. There's no coefficient for u3, so it's 0. And the right-hand side is 2 alpha delta x. That's how you build that system, okay? So that first equation is this, equal to alpha delta x. Now, all the interior points, all the way to point n minus 1, they're the same. They're all the same. All their coefficients are the same. You start with equation at point 2, which is u1 minus 2 delta x squared, x1 squared u2, plus 1 u3, plus 0, 0, 0, 0, equals 0. Then the equation after it, all the way to the last interior points, un minus 1. You have un minus 2 plus delta x squared, etc., un minus 1, plus un. And then the last point, the boundary points are always going to be different. The last point is 1 times un equal beta. Okay. Let's take it up a notch. Consider the steady state advection diffusion equation. D times second derivative of temperature plus U times first derivative of temperature. This equation describes both diffusion and advection. D is the diffusion coefficient, which, like I described one time, it's how molecules communicate at the molecular level, how they exchange information. The first derivative, it describes convection. And the coefficient of convection, U, designates the speed of an airflow or some liquid flow. And that determines the speed at which information is carried by the fluid. So that's going to be your bread and butter as chemical engineers, the advection diffusion reaction equation. With the reaction, you only add a source term. Okay, so you're given this equation. It's a boundary value problem because there's space in it. You're fixing two boundaries. At the left, alpha, and at the right is beta. Now you are to apply the finite difference method to discretize this equation. This is a classic exam question. Okay? Use second order center differencing on all derivatives. You have all the ingredients to do this. You have all the ingredients to do this. Okay? And you assume a grid of endpoints. Okay? Spacing delta x. You assume you have all your xi's. Your T1 is equal to alpha, and your Tn is equal to beta. That is given to you. Okay? So that's our setup over here. I would always start doing the discretization in the middle, at an interior point. Can you do it? Give it a shot. Go back to your notes, use your finite difference formulas, or like 2 tables with those formulas. And only 2 of those formulas apply here. Okay, so take that equation, apply it at point I. So it will be second derivative at I and first derivative at point I. D and U are constants, parameters, they're constants.
I don't really worry about them that much, basically.
Yeah, they're just coefficients, like the heat transfer coefficient.
Oh, sorry, okay.
No, you will be told that those are fixed coefficients, okay? So we kind of did so let me help you a little bit, okay? I'm going to go back and show the discretization here. One moment. Okay. So we're going to need you're going to need this discretization, okay? And so forget about beta over here, but this is the discretization for the first derivative. And the discretization for the second derivative is this formula, okay? Hold on. Just give you formula. I can't find the formula now. Yep. Okay, so that formula. Okay, so that's the formula for the second derivative, and the formula for the second derivative is the one at the bottom. The formula for the first derivative is the one above, but change the indexing, okay? Just put those formulas in. Take a chance. Take a risk. Pardon me? Yes. And you can tell that, Todd, by looking at the dimensions. You have a delta x squared. In a second derivative at the bottom, you're always going to have a delta x squared. In a third derivative, you're always going to have delta x cubed at the bottom, in the denominator. Yeah?
Okay, so one thing I don't understand is that dt over dx is the rate of change of the temperature as we go along the rod, right?
Mm-hmm.
So how is it that that is an estimation of the rate of change while also the temperature at that endpoint is just beta? How is it both the value and the derivative at the same time? Beta.
No, you know the rate, because you can, so when you turn on your heat stove, you're fixing just the rate of change, not the temperature. So when you turn it on, it's emitting heat at a fixed rate. But then that temperature keeps on rising, but that rate is fixed, and you can measure that.
So that's not actually the temperature, that's just the temperature's getting off.
It's a rate, it's a heat flux in that case, or just a rate of change. So sometimes you can measure, so think of flow rate, right? So you don't know the velocity necessarily, but you know the rate of the how fast the velocity is coming in. Okay, how fast the flow is coming in. Okay. But here, we don't have that boundary problem. Right now, I gave you those just to know what to do with the first and second derivative. So this, okay. So this is how I would do it. At point I, you take that equation, apply it at point I. You approximate the second derivative with a second order approximation. To be consistent, we also need a second order approximation for the first derivative. Okay? If you put in a first order approximation, like ti plus 1 minus ti over delta x, or a backward I minus ti minus 1 over delta x, that's still fine, but you're committing a first order error in that case. Okay? So to be consistent with the error committed here, you need to commit a second order error here. And that's it. That's your discretized equation. You rearrange it. Yep, that's it. You just rearrange it because my unknowns are ti, ti minus 1, and ti plus 1. So I put it coefficient times ti minus 1, coefficient times ti plus 1, ti, coefficient times ti plus 1 equals 0. So standard linear equations. And at the boundaries, clearly T1 equal alpha, Tn equal beta. How can I make this harder? I'll put a Neumann condition on the right. What will it change? It will change either, it will change the equation on the right. If I put a Neumann on the left, it will change the equation on the left. It will not change the interior equation. I could choose a different discretization for those. I could choose a third order. Okay? Still be the same procedure. You apply the discretization, get that system of equations, write it in matrix form, and solve it. Yeah.
If you did do that, you get ghost points or ghost points.
So yes. So as you approach the boundaries, you might get ghost points. In that case, one strategy is to actually change that discretization to become one-sided, like Miles was suggesting. So there's an infinite number of possibilities of what you can do here. We're barely scratching the surface, but this gets you a very long way. And you will be thankful you have these notes once you hit mass and heat transfer, okay? Because you have a way of doing them, okay? And you write this in matrix form, and this is what you get. Nonlinear boundary value problems. Okay. So far, we did linear boundary value problems where the discretization led us to a system of linear equations. Okay? If you remember, back when we did nonlinear solvers, you asked for an example of a system of nonlinear equations. And the problem I gave you was a heat transfer with radiation, rod with radiation problem. That resulted in a system, large system of nonlinear equations. We're going to revisit that. Okay? So in general, the boundary value problem you obtain or you're dealing with might be nonlinear in the dependent variable. So here's an example of a heated rod with radiative heat transfer. As you can see on the right-hand side, there's a t to the power 4. Okay? So still the second derivative for temperature, which describes heat transfer or the heat diffusion. But now this rod is exposed to a radiating environment. Okay? So if you discretize this at any point, at an arbitrary interior point, let's see what you get. So this is the formula for the second derivative up there. Okay? So go ahead and try to discretize this at point I and tell me what you obtain. Yeah. So now you can see how complicated this can get. You know, I could throw in a Dirichlet and Neumann condition here. I could throw in a first derivative in the equation, but you have all the ingredients to do that. Apply the finite difference formula to the second derivative, the first derivative, right-hand side, obtain a discrete equation, and see what we can do with it. Okay? So that's the formula for the second derivative up on the left, upper left corner. Equal. Yes. Don't forget the powers. Yep. Okay, so now simplify. Yep. Yep. So what is this equation? Is it?
It's going to be a residual.
Yeah, it's a nonlinear equation, right?
Yeah.
Okay. So we got our first nonlinear equation here. And simplify it, multiply by delta x squared, combine all the terms that you can combine with each other. Okay? Okay. Yep. Okay. So, okay.
It shows up
So,
non-linearly.
exactly. Okay? That's it. Okay. So if you apply this equation at point I and you discretize, so the right-hand side is just simply applied at point I, so you get this ti to the power 4. And the left-hand side, you discretize that with the approximation of the second derivative. You simplify by multiplying by delta x squared, you get this equation, and you're like, well, this is a nonlinear equation in ti. Okay, there's ti and there's ti to the 4th. Okay? So from now you can tell, well, yeah, we cannot have a system of linear equations here. What we're going to have is a system of nonlinear equations, which we know how to solve using fsolve. Okay? So the next step would be to define the residual at an arbitrary interior point I. Okay? If you remember, when we did this problem in the nonlinear solvers, we had to program the residuals at the boundary and at the interior points. Okay, so we're going to do that again here. But at any interior point, the residual is simply you take that nonlinear equation, put everything on the left-hand side, so you get ti plus 1 minus 2ti plus ti minus 1 minus alpha delta x squared, etc. Okay, so that's your residual at any point in the inside of the domain. Now you still need residuals at the left and at the right. Okay, and those are actually the easiest but the most confusing, as I remember from last discussion. So at the left point, sorry, I have a little typo over here. Sorry, let me fix that. Okay, so that's T1. Okay. Okay. So at the left point, T1 is equal to T left. That's my equation. It's a linear equation. That's fine, but you can define a residual for it. R1, still another typo here. I'm always 0 indexed for some reason. Okay, so R1 is equal to T1 minus T left, right? So that's the residual function at the left boundary. And same thing for the right boundary. Okay? So now you have n residual functions with n unknowns. You plug those into fsolve and you can find a solution. Okay? However, you get a large system of coupled nonlinear equations. So let's see if we can solve this together. We'll create a new notebook. Okay. Say, call it nonlinear BVP with Professor Saad 2023. Okay. I'm going to take my boilerplate from over here. And I also need fsolve. So from scipy.optimize, import fsolve. Okay? This is actually, in many ways, easier to implement because it really doesn't have any matrices that you're implementing. All you are implementing are is a subroutine for residual functions. Okay, so let's start by setting the number of points, length of the rod, then T left, let's say 300, T right is 200, T infinity is 500, okay? And then alpha, that's the coefficient, or call it A, whatever. Let's do 10 to the minus 8. We need delta x, so we define a lin space. You can copy that from the previous notebook, that's fine. And then dx is x1 minus x0, okay? Okay. So now for fsolve, we need a system of residual functions, okay? So we're gonna pass that system as R1, R2, R3, all the way to Rn, all the n residual functions. So the routine that generates my residual function is gonna return a system of residual functions, okay? Just like we did. So we're gonna define residuals for the heat transfer problem. And T's, these are the temperatures, okay, that we assume. Now remember, we're going to assume that because this is a system of nonlinear equations, then the solution in that fsolve is the system of temperatures, T1, T2, T3. And every time fsolve calls the residual function, it's going to pass a vector of temperatures, okay, a vector of that unknown. So you can just rely on that as being your input, okay? So here's how I'm going to do it. First, I need the size of that, which we know up there it's n equal to 100, but I can deduce it from here as well, len of t's. And then R, my residuals, okay, is going to be, I'm going to initialize it with a with an NumPy array of zeros of size n. Right, so that's going to store R1, R2, R3, all the way to Rn. Okay. Then I'm going to loop. Over the entire range of interior temperatures. Okay. So I'm going to go for I in range of 1 to n minus 1. Now remember, Python is indexed from 0 to n from 0. So our points are going to be R0 to Rn minus 1, right? So in our range, we're going to start from 1 to n minus 1 so that the last interior point is indexed at n minus 2. It's kind of a bit confusing that way. But, okay, so my residual functions, these are, I'm going to implement these now. Just simply as is, just like this, ti plus 1 minus 2 ti plus ti minus 1, etc., right? Okay, so how do I do this? It's simpler if I grab if I grab these temperatures as Ti minus 1 and call that Ti minus 1, okay? And Ti is simply Ti, and Ti plus 1 is Ti plus 1. I'm just storing those into temporary variables for easy typing, okay? But literally, this looks exactly like that formula that we have over there, okay? And finally, Ri is simply whatever that formula was, minus 2 Ti, minus Ti, sorry, Ti plus 1 minus 2 Ti plus Ti minus 1. Okay. So it is Ti plus 1 minus 2 Ti plus Ti minus 1 minus alpha times dx squared, right, times Ti to the 4 minus T infinity to the 4, right? Correct? Yep, minus alpha delta x squared. Okay, so that covers all the interior points. The first point at the boundary, which in our slides nomenclature is R1, but in Python is going to be R0. Okay, that is simply R0 is equal to T0 minus T left, right? If you look at the slides, our R0 or R1, the first was T1 minus T left. Okay? Same thing, yes?
Your residual function, is that supposed to be Ti minus 1 or Ti n 1?
Yes, that's correct. Yes, thank you. Right now, it looks like Tim. Okay. And then the last point, thank you for catching that. So last point is R at minus 1, which is equal to T at minus 1, the last point, minus T right. Okay? And then we're going to return R. That's it. So now, yeah?
Where is T defined?
T comes in, it's T's. Okay, let's call it T. Okay. These are the temperatures. Thank you, Miles. Okay, this vector of temperatures comes in through fsolve. So once you're in the residual function, you assume that you have access to Ti plus 1, Ti minus 1, and Ti. Okay? I know it sounds like magic, but it's really not. Okay. Now the initial gas, T initial, I'm going to make it equal to T infinity. Or I can make it equal to T left or T right, it doesn't matter. And then my solution is equal fsolve. And I'm going to give it the residual function, the residual routine, and the initial temperatures. Let's see, plt.plot, xsolve, plt.grid. Yay, look at that. It's less code than the previous problem, but it does the job. This is a system of nonlinear equations, highly nonlinear for that matter. And I was able to converge it, okay? Was able to converge it. You can change the values, etc. Okay, you can do 400 over here. So it's doing something, right? Change it to 400 over there. You can change the heat transfer coefficient. Okay, so if we make this a little larger, so 10 to the minus 5, they're going to be more flat because radiation is going to just take over and it's going to dissipate the heat everywhere in the rod. Okay? So it's solving it, and it's doing it correctly. Okay? Pardon me?
Oh, I just said you're speedy fast.
All right, does this help a little bit? Nope.
So I just want to so I had a question, but I think I understand it. So the reason Jesus Christ, hold on a second. The reason R0 and R at the end is T0 minus T left and T minus 1 minus T right is the T is our formula here, but we know that this equals T left.
No, this is the residual at I, but the residual at
those equals that. So
yeah, because you know T1, yes. So the equation, here's how to think about it. You first ask, what is the equation at the left boundary?
it's this equals T.
No, it's T1 equal T left, not this one. Because it's specified. It's specified. If you apply this one, you're going to end up with a ghost point. Yep. That's the equation at the left boundary. Okay? So always start by saying, what is the equation at the left or the right boundary?
It's giving me an error saying there's a float.
No, it's not callable. So you're trying to call. So scroll up a little bit. Let's see. Do you mind? So fsolve residuals.
Wait, I'm getting you're saying float 64
I
error.
forgot the
Times. That's right. It's calling dx of. You got it.
Looks similar, but not the same.
Okay, I'll come back to you. Let me make one last, one more thing, guys. One more thing, just one last slide before you go. One last slide, okay? We have next Tuesday, but this is, I want you to see this in class before you go to the homework, okay? Now, you can add a Neumann condition here. And all you have to do is do the discretization like we did, add the right boundary. So you'll get the same residual on the interior, same residual at the left, but your residual at the right boundary is a little different. Okay? At the boundaries, ask yourself, what is the equation at the boundary? What is the equation for the temperature point at the boundary? If it's given to you, then the equation is T1 equal T left. If you have a Neumann condition, you play with the discretization, then this would be the equation for the temperature at point N. It has terms in terms of N minus 1 and N, etc. But that's the equation. From that, you build that residual, okay? All right, have a nice weekend. I'll see you on Tuesday.